All right, as promised, here we go with kites, second half of 6-6. All right, so the last one in the little family tree here is the kite, and the kite is really not a bad name for what it is. It's a quadrilateral that has two pairs of consecutive congruent sides. So, and kind of like the sort of restrictive definition of trapezoids, and this kind of goes along with the same controversy, that's all it can have. It can't have all four sides congruent. So these have to be two distinct pairs, or in other words, exactly two pairs of consecutive congruent sides. It can't have four. It can't have more than this. So in other words, this single tick and this double tick have to be different, even though that notation by itself doesn't mean that. You have to assume if it's a kite, these are actually different. Okay, enough about that. All right, and we get two new theorems, and yes, finally we get to 6.26, the last theorem of Chapter 6, which has been chock full of theorems. All right, the first one is the diagonals. This should kind of remind you of rhombuses. Diagonals in a kite, just like rhombus, the diagonals in a kite are perpendicular. The other one is that these angles like at P and R, the angles, again, they turned it when they went from this example to this example. Even from here to here, they turned it. This kite looks kind of funky, but it's a kite. The angles that connect kind of the, one of each different side length, the angles there, the angles that are not included in congruent sides, but the other angles here, like L and J, that pair of angles has to be congruent. And notice, it says exactly. So K and M, we know, are not congruent. That can come in handy later. J and L here have to be congruent, K and M are not. In this, if you want to see what that would look like here, I know that big angle C and big angle A have to be congruent. I know that big angle B and big angle D are not congruent. Here, Q and S are not congruent, but P and R are congruent. Note the pair of congruent angles is included between non-congruent adjacent sides. I think I said that. You might want to rewind that and listen to that again, because it'd be easy to confuse that and think of that the other way. All right, another construction, and I left my compass right here close. All right, construct a kite given that FG is a diagonal, so we need like F, K, G, J or something like that. We need the kite to go around this way. This is not a side of the kite. This connects two corners of the kite in the middle of the kite. Well, we just learned that the diagonals of the kite, and that's what this is a diagonal. This has to be perpendicular to the other diagonal. Let's construct a perpendicular. Does it say this is a bisector? It doesn't. I happen to know that it is a bisector. Wow, we could have done that 27th theorem, that this thing here is the midpoint of BD, but it's not the midpoint of AC. I really want to use that. Well, okay, we can do this. BD, I'm gonna use that as being kind of the same purpose as this diagonal here. Notice that because of these other sides that are congruent, that are kind of pointing or attached to BD, I know that BD is the base of an isosceles triangle on both directions. Kind of like, there's an isosceles triangle here to C. CBD is an isosceles triangle, and ABD is an isosceles triangle. So let's just make isosceles triangles that hit that. All right, so I'm going to make an isosceles triangle where FG is the base. All right, so I need a length where I can decide to draw away from point F. And so I got to make it bigger than half, right? I got to make it kind of, so it's going to reach. We're going to have a T-Rex problem here. So I picked some random distance I want for these sides over here. Let's say it has to be that far away from F, and it has to be the same distance away from G. I got to get it right on there, so it looks relatively reasonable. Okay, so this point here, I could say is the vertex of an isosceles triangle that has FG as a base. And it's hard to get right on there. Okay, great. I know those lengths are equal because I did what I just did with the compass. All right, and now I have to make the same kind of thing going on the other side, but it has to be different. So I have to definitely change the compass, and I just do the same thing over here. Let's make a random swoosh. Leave it the same on this one. So of course this one has to be the same now once I've done that, but because I need another isosceles triangle. But this isosceles triangle has to be a different size than this isosceles triangle. Those lengths here to the left have to be different than they were to the right. Oh, it's hard to get that right on there. I don't think it's absolutely perfect, but you get the idea. I constructed it so that had to happen first. I made those the same compass size, and I changed the compass size so they're different over here. But then I made this one equal to this one. It's kind of like I was going to do the football thing, and I was going to make a make the full swoop, but I only need to make one cross, because I only need to do one isosceles triangle. Right, so that's going to be a kite. Diagonal FG. All right, find the value of x given diagonal. All right, so I don't need the compass here for a bit. Oh, I can only get it away that far. All right, so what we found out about this thing, oh, look, this is a mid-segment. This is a midpoint, and this is a midpoint. So when we join midpoints, not only is this parallel, okay, yeah, because we're talking about a trapezoid, this is parallel, and this length here is the average of these two lengths. The way that formula worked was the 10 is equal to, if you look at it in the theorem thing, it said this way, half of the sum of the other two things. So 2x minus 4 plus x minus 3. This is not the easiest first example I can think of. The easiest first example I can think of, and notice these don't have to be, okay, I'm just going to say this. These don't have to be isosceles. This one we're looking at now really doesn't look isosceles. It looks kind of, you know, non-isosceles. This little length up here was 4, and this big length down here was, I don't know, 14 or something. And we picked the midpoint here and connected to the midpoint here. And I don't even know what these lengths are. I don't really care. I just care that they're midpoints. How do we find the length of this mid-segment in here? I'll call it M. Mid-segment M, the length of that is just the average of, or in other words, half of 4 plus 14. So that turns out to be halfway between 14 and 4 is 9. Yeah, so that's what's going on. Here I'm doing an example with algebra, so I thought I'd just show you that quick, because sometimes they're that easy and sometimes they're this hard. This is kind of the two extremes of this thing. To get rid of this half, I kind of like doing this. Multiply everything by 2. Let's combine these while we're at it. 3x minus 7, so 3x is 27, x is 9. Great. Okay, proof. Let me copy in the basics. Okay, I only do a little bit of cheating there. All right, we know we have a trapezoid, and it's marked with the parallels, PQ and SR. And we know that PS is congruent to QR. Okay, well that should tell us something. We have a trapezoid, and we have the legs. These non-base sides are congruent. Hello, there we got a theorem about that. If non-base sides are congruent, what kind of trapezoid are we dealing with? Back to here. That is an isosceles trapezoid. So I hope it's called, I haven't looked at the sheet, I hope it's called Isosceles Trapezoid Biconditional. We're going to use the Isosceles Trapezoid, forgive me if this is not correct, Isosceles Trapezoid Biconditional. I don't want to call it ITB because that was about Isosceles Triangle. It was 621, 622, that kind of stuff. That biconditional, those two we zip together as a biconditional. Says, yeah, I know this is an Isosceles Trapezoid. So that tells me this whole angle here is congruent to this whole angle here, and this whole angle here is congruent to this whole angle here. Now, I don't know which one of those would be useful at first. I just got so excited about seeing that side congruent to that side, I thought, okay, let's go to town and say this is all true. So angle SPQ is congruent to angle RQP. Got to use 3 letters on these because there's so much else in this diagram. And same step number. I'll just say it all at once because it's the same. It's the same reason, QRS. Now that's not what we're looking for, right? SPR and SQR. So we're going for these little ones up here and up here. So that's probably, there's probably some overkill in there, but all that's true for the same reason. Okay, so yeah, that's not what I want. What I want is this little one here and this little one here. Okay, I don't quite have that yet, but is there a way I could get, well, this would be great if I could get these to be congruent because they're parts of bigger triangles. Let's say this. Let's hope for this right now. Let's say SPR, angle SPR is part of triangle SPR. That would be wonderful. If I could get triangle SPR to be congruent to, I guess if it goes SPR, it's going to have to go RQS. Triangle RQS, because then this reason would just be, well, because they belong to those bigger triangles. That's lovely. All right, because what I'm seeing in this already, look at this. With those triangles I already have the double arc angles. So there's an angle. I already have PS and RQ, so there's a side. And so I'm either going to look for SAS or AAS or ASA or something like that. Anything you can see. Oh, look. Oh, yeah. Oh, good. Look at that right here. We have reflective. SR is congruent to itself. Does that help with this? It's actually easier if I write fast. Okay, maybe not. I thought it was easier if I wrote faster. Now looking at triangle, this is hard because they're all overlappy. Triangle SPR and triangle RQP. Now there's some stuff in there that we have to ignore because it's like these big arc angles up here I don't really need. And there's overlaps and there's cut segments and that kind of stuff. But in triangle SRP, this thing right here, what's marked is the double tick angle, the double arc rainbow, sorry, the double tick side, the double arc rainbow angle, and the single tick side. That to me looks like side angle side. So that's what we have. Side angle side, and that's enough for congruent triangles. And then we can get the triangle angles we need from CPCTC out of those. All right, couple more here. They're telling me it's a trapezoid. They're telling me FG is parallel to AD. Thank you very much. I could have done that with slopes by myself. And they're saying, find the coordinates at point G. Well, they're telling me it's a trapezoid, and FG is parallel to AD. I'm guessing that in the trapezoid we're talking about, it's going to be AD that's parallel to BC, not that AB is, sorry, yeah, A. Did I say that right? It's going to be that these are parallel, AD and BC, not AB and DC. I don't really care to do that right now, but I'm pretty darn sure those are the slopes that are going to be parallel. So if those are all parallel, and is this a midpoint here? Oh, good. Yes, it is. 0, 8, 9, 8, 18, 8. Perfectly horizontal midpoint. Then it's got to be a midpoint down here, too. I bet you could have figured that out. So really what I need to find the coordinates of G, really all the things we've done this year that are calculation-based that end up with a coordinate has been midpoint. So I need the midpoint of DC. Midpoint of DC is this great big averaging thing where we're adding coordinates and dividing by 2. And we're finding the midpoint between the D and C for X coordinates and for Y coordinates. So the D coordinate is 1, 4, and the C coordinates are 20, 0. So this is 21 divided by 2 and 2. So that's like 10.5, looks pretty good, comma 2, looks like it's right in the line there. Great. All right, given that LON is 34, which is this big thing, and LMN is 44. Okay, so this big guy here is 34. This big guy here, and of course it's different, it's not congruent to that one, it's 44. We were told in the chapter that this whole angle and this whole angle have to be congruent. Whoops, don't want that. So we can figure out what they are right away because we can know that the whole thing adds up to 360. So what's left? 360 in the whole quadrilateral minus 44 plus 34. Yeah, calculation time. This is 78. So the whole thing left is, gosh, I hate doing this in front of the camera. 282, is that right? 282, 290. Yeah. So 282 is what's left between these two angles. So each one has to be, MLO included, they have to be 141. And MLP, okay, if this is a isosceles triangle, if this angle is 44, we can figure out what these are. That angle, I'm using new marking scheme, sorry. That angle is congruent to that angle. If this is 44, the rest of the 180 has to add up to these. They have to be congruent. So I believe they both have to be 68. You can check me on that. 68, 68, and 44 ought to make 180. All right, just a couple left here, but I'm about to run out of time again. Construct the median and mark the diagram with known information. All right, so I need midpoint here, midpoint here. Let me do those two midpoints. You should know how to do that. I'm going to do that by footballs. Yeah, so I just made the compass bigger than half. I stabbed at D, made an arc, stabbed at A, made an arc, and then I whoops. And then I try to do that. I connect these two ends of the football, and I just found the midpoint of AD. Let me do the same thing with BC. Oh, I can do it so you can see it. Ah, come on. I can do it so you can see this time. So I make a swoop from C. Oh, I hope that's long enough. I'm running out of time. I make a swoop from B. Oh, please be long enough. I'm going to assume that hit because it takes me forever to do this. And we're going to hit end the video. So there's my two midpoints. I will connect them, connect this midpoint to this midpoint, and that is the median. I discussed what was congruent, so I'm going to say that. Construct an isosceles trapezoid given that AB is the base and AD is a leg. Okay, so it's going to look something like this. I'm going to, I just decided I can't do that in 16 seconds. I'm going to leave that for you for homework. Okay, see you in class. Okay, I realized that sounded like a bit of a cop-out, so I went ahead and did it. So this is what it looks like, but you'll have to see the process in class. Boom.